everything over here on the board. Writing all this down on a sheet of lined paper would be very helpful. So what does it mean to solve an equation? Anytime you have any equation, what does it mean to solve it? So let's just take a simple equation like 3x, like 3x plus 4 equals 13. Right? What does that mean to solve an equation? Solve for x. What does that mean? In this particular case, it would not be a coordinate. Very, very good guess, though. As if it was a coordinate, you'd have to have x and y. Wait, who said coordinate? Was that? Yeah. Oh, you did, Victor. Sorry. Yeah, so it would be a coordinate if there was an x and a y, but this is just an x. I suppose you could say that you're finding a coordinate on a number line. Then that'd be fair. It could be, a point on a number line. So we're solving for x. What does it mean? You're finding a number that makes the equation true. That's ultimately what you're doing. If you just walked up to somebody and said, hey, find a number to plug in right there so that it's true, there's any number of ways that you can approach that problem. It just so happens that algebra is a technology invented back in like the 800s or 900s that says if you want, you can do anything you want so long as you do it to both sides. So what I just wrote right there, -4 on both sides, that's the technology called algebra. It says you're allowed to do anything you want to both sides. And that technology inherently is about cancellations and destruction, where you're destroying things from left and right. And then ultimately you're getting that x all by itself. So you keep on rewriting things, and then you do it one more time, and you're using opposite operations. So since x is being multiplied, you would divide, and that cancels it out. So this whole notion of what this is called algebra. It's a process of destruction where you do the same thing on both sides, utilizing inverse operations that cancel things out. But that's just a method. What we're really trying to do is say, well, I think 3 would be a good guess. Like, not just a guess, but it's correct. That now this is a number you can plug in to make that equation true. So now if I take the 3, something 4 equals 13. If I plug in 3, that'd be 9 plus 4. It better be true. So this right here is actually what it means to solve an equation. Is to find a number that makes the equation true. So this right here is what it means to solve an equation. This right here is just an algebraic process. It's just an algorithm that generates a number that makes the equation true. Okay, what does it mean to graph an equation? So now let's say that I had y equals 3x plus 4. What does it mean to graph this thing? What does it mean to graph it? Is it weird to have the question asked in such an open-ended way? Because we're like, well, it's all pretty obvious what it means. I mean, it's going to be a line, it's going to have a slope, it's going to have a y-intercept. But what does it mean to graph it? What's really happening? Yeah, I mean, there's whatever line is going to appear here, which I'll just use the trick, which is that that's the y-intercept, and this is the slope, right? That's just a trick. That's just a shorthand. So I'd have a y-intercept of 4, and then I'd have a slope of up 3, right 1. So I'd go up 3, right 1, or down 3, left 1. So that's just a trick, right, to put down the y-intercept and then put down a couple slope points and then draw a line. But what really is that line?
Any point in that line will make it true.
Exactly. Any point on that thing will make this equation true. We're still talking about plugging things in to make the equation true. So now if I just choose any point on the line, I have 3 points here already. So this would be 0, 4, and then that'd be the point 1, 7. And then down here, this would be the point -1, 1. Let alone the infinitely many other points on this line, which could be decimals and fractions, even square roots, right? I mean, there are coordinates on here that are particularly nasty. It could be like 0.307651 and then 0.42937. Like, there's some really nasty, infinitely long decimal coordinates on this line as well. And what we know is that if I take any of those coordinates, I'll just take this one and plug it in for x and y. Then if I take my original equation here, y equals 3x plus 4, and I plug in 7 for y and 1 for x, I generate a true statement. So what does it mean to graph an equation? This line isn't really a line. It's just infinitely many coordinates. It's infinitely many pairs of points that make that equation true. And that's what it means to graph an equation. Okay, so what's a function? Let's say that my function was f of x equals 3x plus 4. What is a function? Yeah, absolutely. If somebody asks you what a function is, you'd want to say input output, because that's exactly what it is. It's some sort of a machine that takes an input and then creates an output. The input goes right here, and then this entire thing is the output. And each one of those pairs of input-output, you could do it on a table, right? So you've got x, and then you've got f of x, which is 3x plus 4. And you can plug in a bunch of inputs, 0, 1, 2. So then I would have 4, and then 7, and 11. So I have a bunch of inputs and outputs. In and of itself, that might not be super interesting, although it could be. Like if this is the number of hours you work, and this is the number of money that you've got paid. So if you work no hours, you get $4. That doesn't make too much sense. If you work 1 hour, you get $7. That's unfortunate. Anyway, so this doesn't really reflect how much money you get paid. But the point is you have an input and an output. And that's what a function is. So then what can I do with all these input outputs? I mean, how else can you interpret them? What is every input and output? What is each input output taken together? Yeah, I heard somebody say it. It's coordinate. So each one of those are coordinates on a graph, right? So now, again, I take all these input outputs, and then I put all of them onto a graph, and then I say, that's the graph, right? That's the graph of that function, is by running through all these input outputs, you get a long list of coordinates, and then you graph them, and then you say that's the graph of that function, right? So that's what a function is. What are two things you can do with a function? Right? You've got input, that's fair. Input is the x, and output is the y. So that's another way of looking at it. You can say this is your input x, and then this whole thing is going to be your output y. But what can you do with an input, with a function? Ultimately, there's only two things you can do with a function. You can either, or you can. What, Linda? Well, that's true. You can graph it. I suppose you can do a lot of things with a function, yeah. But I mean algebraically. What can we do arithmetically and algebraically with? Well, in fact, it is. One is arithmetic and one is geometric. So what can you do with a function? You can either
Find x or find y.
That's true. You can find x or find y. Yeah, you can solve for x or y. Because like in this equation, you could plug something in for y and then solve for x, or you can plug something in for x and solve for y. That's true. But what's the way we've been saying it from the beginning? You can either plug something in, right? Or you can set something equal to it, right? So if I wanted to, I can plug something in, like the number 5, and I can say f of 5. And then this is a purely arithmetic operation. When you plug something in, you're doing arithmetic, and that's it. Whereas if I set it equal to, then I have something very different. I have f of x equals 3x plus 4. And if I set that equal to 5, okay, now notice I'm using the same numbers both times. And yeah, these are very different things. If I plug 5 in, I'm just doing arithmetic, and I just calculated an output. But if I set something equal to the function, which is the output, then when I do my algebra, which gives me x equals a third, I just found an input. Okay, we've never said it quite like that before. So again, watch. There are two things you can do with a function. You can either plug something in which case you plug in the in which case you plug in the input, do arithmetic, and calculate the output. So if you go from input through arithmetic to the output. Or if you say what the output is, then you go through algebra to get to the input. Right? So that's very interesting, those two different ways of going from input to output. That requires arithmetic. Going from output back to input, that requires algebra. All right, so those are two things you can do with a function, other than the fact, of course, that you could graph the function. How do you find the x-intercept and the y-intercept of a graph? This is a big idea that we talked about from the beginning. So I've got some function now, which I have graphed. So here's my function, f of x. And I'd like to find the y-intercept. I'd like to find the x-intercept. This is the y-intercept up here. This is the x-intercept down here. How do I find those two numbers?
Set f of x
For which one?
For the y-intercept, you plug 0 into f of x, and then to solve for the x-intercept, it's f of x equals 0.
Right. So for the y-intercept, you simply plug 0 in. Plug in 0. Whereas for the x-intercept, you set the function equal to 0. Okay, this builds on the idea we just said. You can either plug a number in or you can set it equal to. And 0 is a very special number. 0, if you plug 0 in, you're getting the y-intercept. And why should that be? Because if you're plugging in 0, okay, you're getting a coordinate that has to fall on the y-axis. Because if you're starting at the origin, you go right nothing, and then you go up, you're going to be on the y-axis. So by definition, plugging 0 to the function will give you the y-intercept. Whereas by definition, if you set it equal to 0, remember what you set it equal to is the output or the y value. Then you're looking at a coordinate whose y value is nothing, which means if you start at the origin and go up or down nothing, you're on the x-axis. So, right, we set f of x equal to 0 to find our x-intercept, and we plug 0 into the function to get our y-intercept. Which one of these is easier to do? Yeah, and this is super easy. Like, super easy. And why is it super easy to plug 0 into a function? Because what do you want?
Because you're replacing the x with a 0, which gives you the direct y coordinate.
Yeah, exactly. Replacing x with 0 is wonderful because multiplying by 0 is nothing and adding 0 is nothing. But more importantly, it's easy because you're just doing arithmetic. Where 0 is a wonderful number to do arithmetic. Whereas setting the function equal to 0 is a little more challenging because now you'd have to do algebra, right? So to be fair, when you look at the difference between these two things, this is something that grade school kids learn how to do. It's just arithmetic. You know, adding, subtracting, multiplying, dividing, squaring, square rooting. Whereas doing algebra is the entire field of study, everything you do from like 7th or 8th grade on, all the way into college and beyond. You're just learning how to solve equations by setting that equation equal to something. Okay, so that's how you find the x-int and the y-int. When solving a word problem, what are the first two things you need to do? The first two things you might want to do are cry. When you're done doing that, get a snack. But when you're done doing that, define your variables. And notice by defining your variables, you're allowing yourself to do everything that we just said up here. I mean, you need a variable to do anything. To solve an equation, you need a variable. To graph a line, you need a variable. To do a function, you need a variable. To set something equal to or plug in, you need a variable. And to solve for x and y intercepts, you need a variable. So obviously, the very first thing you need to do is figure out what's my variable, what does it represent, what are the units, and then you can create your equations. Which again is everything that we've already talked about. You need an equation with a variable to do anything in algebra. And so the very first thing you do in a word problem is get your variables and get your equations. All right. How do you solve a quadratic equation? Oh, goody. Now, by the way, does anyone remember what quadratic means? Quadra? Quadra? What's quadra?
Quad is 4.
Yeah, quad means 4. You probably know a lot of words that start with quadra, like
Quadrilateral.
quadrilateral is a 4-sided shape, like a square or rectangle. What other words start with quadra? Quadruple, yeah, so like quadruple in size. Quadruplets would be not twins or triplets, but quadruplets. Any other words? What about just a quad? Like, do any of you go out driving ATVs? That's called a quad, right? An all-terrain vehicle is a quad because it has 4 wheels. Well, the really weird thing is that yes, quad, one of the roots means 4, but the other root simply means square. And that's what really matters to us, because when you look at a quadratic equation, is there anything about a quadratic equation that has 4 in it? No 4 to be seen. There are no 4s in this equation anywhere. What's quadratic about it is the fact that the word quadra actually means square. Like a square, literally a square. And that's the square right there, the x squared. Because the difference between a linear equation, mx plus b, and a quadratic equation, like if you look just right here, that's mx plus b in disguise, right? That's mx plus b. That's a linear equation. So that part right there is linear. And what makes this thing different is this thing right here, which is the quadratic term, which literally means the squared term, right? So That's a quadratic equation, ax squared plus bx plus c. And so how do we solve it?
Define A, B,
Like
and C.
I'll give one here. X squared plus, we'll just say 8x plus 15. And I'm going to set that equal to 0. How do you solve such a thing?
Set your variables A, B, C, and then you plug it into negative B plus minus B squared minus 4AC.
That is
Over 2A.
right. That is certainly one thing you can do. You've got your quadratic. It's set up in standard form where you've got A and B and C. And you could always plug that into the quadratic formula. So negative B plus or minus square root of B squared minus 4AC over 2A. Now, how long have humans had the quadratic formula? Well, I mean, at least back to the first person who wrote an algebra book, which is around 800 AD, and that was all, oh, what's his name? I'm forgetting his name right now, but he gave the word algebra. So we've had it at least since then, but we've, even ancient Egyptians and people in ancient Greece, they were able to do this as well. So we've had this for a very long time. And what does it actually give you? What is the actual output of that formula? When you solve a quadratic, what do you find?
The possible x-intercepts.
Exactly, the x-intercepts. So when we look at a quadratic, which is a parabola, and these two x-intercepts here, that is what this formula is giving. It'd be really nice if instead of calling it the quadratic formula, what if we called it the quadratic x-intercept formula? That would give people a little more insight as to what we're talking about. This quadratic formula gives you the x-intercepts of a parabola. So, if it spits out two answers, you have two x-intercepts. And if it only spits out one answer, then you only have one x-intercept. But if it spits out no answers at all because it's imaginary, then you know that your quadratic is floating up above the x-axis. So yes, going all the way back to a former question, what does it mean to, did we do that in a previous question? What does it mean to solve an equation all the way back to here? And Victor said you're finding a coordinate, which was on a number line. But when you solve a quadratic, you're finding x-intercepts. In fact, always. Any equation that you solve, you're solving x-intercepts. Even if you go back, Victor, I take it back. Maybe I was a little too quick to say that you needed two variables to find a coordinate. It's not exactly true, because if I just graph 3x plus 4, the x-intercept is still the solution. So my solution to 3x plus 4, my 3x plus 4 equals 13. I have to move that 13 over to the other side. That's minus 9 equals 0. Yeah, there we go. By moving the 13 over to the other side, well, if you did, hold on, let me actually show it so everybody can see it. If you actually take your original equation and move all the terms to the left so that it's equal to 0, so that would be 3x minus 9 equals 0. Any equation at all, if you set it equal to 0, and take that thing and plug it into Desmos, the x-intercept is going to give you the solution to that equation. We talked about that once, right? But that's an important idea. Take any equation in the world, set it equal to 0, and plug what you have on the left into Desmos or a graphing calculator, and the x-intercepts are the solutions to the equation, right? So that's a big idea. How do you solve a quadratic equation? You're finding the x-intercepts. You're finding the values that you can plug in to make the equation true, but you're also finding the x-intercepts. Okay, next, what does shading mean?
Everything outside of her if it's a shaded area, then it's not part of a true equation. Everything inside the shaded region would make the equation.
Yeah, anything in the shaded region makes the equation true. Because again, going back to the beginning, what are we looking for? We're looking for numbers you can plug into equations to make them true. What is the graph? A whole bunch of dots or a whole bunch of coordinates that make the equation true. And what does shading mean? It means those points make it true. So if I have 3x plus 5 is greater than or equal to 14, and then I do my algebra, and I get 3x is greater than 9, and then finish my algebra, and I get x is greater than or equal to 3, when I draw a number line, starting, well, here's 0, here's 3. And I'm going to close the circle and shade to the right. What I'm saying now is if I choose any number from in there, I can plug it into this original inequality and it will be true. Because ultimately, that's always what we're looking for. We're looking for numbers we can plug into equations or inequalities that make it true. So we then take that and we write it down in interval notation. And what is interval notation? Interval notation is it's a number line. Interval notation is just a lazy person's number line. so that you don't literally have to write a number line. But an interval notation is still just a number line, and that shaded number line is telling you all the numbers that you can plug in to make it true. So what is shading? Yeah, shading represents truth. It represents all the numbers that you can plug in to make the equation true. And therefore, what is a graph? You know, any graph that you ever look at, whether it's a straight line or a parabola, it's just, yeah, it's just shading. That is what a graph is, it's shading. You know, if you shaded all those points, just like you shade a number line. There's no difference between shading a graph and shading a line. It's still shading, and it still represents truth. All right. When would you need to use a log? Why were logarithms invented in the late 1500s by John Napier? What were they trying to solve? What are you trying to solve for that would necessitate a log? Like, uh-oh, everybody, we're trying to solve for blank. Somebody get a log. Yeah, for exponents. Exactly right. We're trying to say, what if x is in the numerator? I'm sorry, what if x is in the exponent? Right? Because only when you actually put a variable in an exponent do you need a logarithm. Everything else, if x is just a base, you don't need a logarithm because x is a base. Like 3 times x, x is a base number. So you don't need a log to solve that. But as soon as you put a variable in an exponent, that's what would necessitate a logarithm. And some logarithms you can just guess, like 10 to the power of what is 100? 2. And so you would just say x equals 2. There's not really any algebra going on right there. You just go from the problem statement to the problem solution, and then you're done. But if you had something more like 2 to the x equals 100, then you'd have to rewrite it as a logarithm. So that'd be log base 2 of 100 equals x. And notice we've already solved for x. That's the brilliance of a logarithm. Within one step of transformation, you've already solved for your variable. Your variable is all by itself already, all by itself on one side of the equation. And so then this thing represents the answer. And using the change of base rule, you have log 100 over log 2. And you type that into your calculator, which has all those things stored in it. And you get your answer. Okay, so yeah, when would you need to use a log? When you're solving for an unknown exponent. And then finally, what is a system? Well, that's true. That's the solution to a system, is the coordinate that makes all the equations true. What's the system itself? More than one equation, more than one graph at the same time. So if you have more than one graph at the same time, like let's say I have this parabola and I have a line going through it, that's a system because there's 2 equations being graphed simultaneously, and the solution would be the 2 points of intersection. Or let's say I've got another parabola going upside down, then that's a system because there's 2 parabolas and the points of intersection are the solution to the system. Or if I have a parabola and a line that doesn't intersect it, you would say, well, that's a system. There are 2 equations graphed on the same graph, but they don't intersect, therefore there's no solution. There's no coordinate in this infinite universe that would make both of those equations true simultaneously. A coordinate would either make neither of them true, or one of them true, or the other one true, but there's no coordinate that makes both of them true. Yep. All right. Well, folks, those are all the big picture ideas that we talked about from the beginning of the semester. I hope that that's helpful to see all that at a glance, to know kind of what we were talking about. You know, it'd probably be fun if you could do something like this on the first day of class. The only tricky thing is like the log, you know, if you've never studied logs before, then it'd be tough to really say that. But, well, what do you think? Would it be helpful to see something like this on the first day of class?
Yes, because it tells you what you're doing.
You know, like a big roadmap and a big conceptual overview. Yeah, even if it's a little confusing, if you're like, well, I've never seen this before, it's a little confusing, at least you still have an idea of where you're going. But these are all the big ideas. All right, so today's excitement. Today is, that's the wrong calendar. As always, I have the wrong calendar. Well, that's okay. Today is going to be our day to review the final exam. So you all have your practice final with you. And next week, you're going to come to class, and we take our final exam at the same time. Right? So if anybody wants to write it down, our final exam is Monday, or our next class period. So the final is Monday at 8 a.m. Now, the final is a cumulative final over the whole course. And it's a common final, meaning every Math 150 course at Gateway takes the same exact final. So whether you're in my 150 class or another 150 class, all the students are taking the same test. The practice final that you have in front of you, I created to give you sufficient practice for the types of questions you'll see on the final. So if you can do all the questions on your practice final, you'll be able to do all the questions on the real final. When you come to class that day, finals are structured by the college itself, not by me. And everybody is supposed to be given an hour and 50 minutes to take their final exam. Now, how many questions are on the test? I think there's only 20. So 20 questions over 2 hours, 10 questions per hour. What is that, like 6 minutes per question? I mean, it's a comfortable amount of time. But provided no one's trying to come in here, I'll just let you keep working. But you should count on having 2 hours. But if we're lucky and nobody else is trying to come in the room, you could work longer. Yeah, that's your final. Okay, so I'm going to post an online course survey, probably this weekend, or maybe it's already open. But please take online evaluation before coming to class on Monday. Essentially, taking that online evaluation is your ticket to get your final exam. So when you come in, all I see is a list of who's taken it and who hasn't. So if you haven't taken it yet, when you come in that morning, I'll say, please go take the evaluation on your phone. You can pull it up on your phone. I'll let you use the computer if you want. But that's your ticket to get your exam. I really appreciate your feedback. It helps me to make decisions about how to structure the course differently or improve upon it. So I really appreciate you all taking the time to do the course evaluation. It takes probably 5 minutes to answer a few multiple choice questions and then fill in some questions as well. Chelsea? The final exam is right here in the classroom, and it's just going to be a piece of paper stapled together. Yeah. All right. Well, I think that's that. Any questions before we start going through the final exam? Okay. Got some jokes for you. I spoke at a nursing conference the other day, so I'm going to tell you the jokes I told to the nurses. There were 3 of them that I told, so here you go. Everybody ready? The first one, how many nurses does it take to screw in a light bulb? None. They get the nursing assistants to do it. That may or may not be funny to you. The conference was about nursing assistants. That's a whole field in and of itself as opposed to nurses. Okay, let me try to, what's that? Yeah, CNAs, exactly, certified nursing assistant. Okay, next one. Statistically, 9 out of 10 injections are in vain. Thank you, Josh. Thank you, Josh. Okay, last one. You'll all love this one. So a nurse tells the new parents, oh, you have such a cute baby. And the mom says, oh, you tell all the new parents that. And the nurse says, no, I only tell that to parents with cute babies. And the mom says, well, what do you tell the parents who don't have cute babies? And the nurse said, oh, he looks just like you. All right. I think that's a great joke. So, folks, working our way through here, we have how many questions? I believe 20. Did I put on the practice? Yeah, I sure did. Yeah, 20 questions on the final. So I think we have time to go through all of them. Although, I mean, it's not like we necessarily have to do both of those questions. I gave 2 just so you can see 2. But how about in this particular case, we'll just do 1 of them. Do you want to see the one on the right or the one on the left? The one on the what?
On the left.
The one on the left. Okay, everybody, so we're on number 1. So now let's talk about how you're going to show your work. So on the final exam, definitely you need to show as much work as possible. You know, don't do any shortcuts, don't do it all in your head. You have to show all of your work to get full credit. So if you did this problem and somehow miraculously you just wrote down the correct answer, I would say to myself, well, gee, I mean, they did something to get the answer. Maybe they graphed it on their graphing calculator. Maybe they did a bunch of work in their head. But I wouldn't give you full credit for that, right? In order to get full credit, you have to show me logically, step by step, a full argument of how you got your answer. So make sure you're showing all of your work. So what do we do first? Right, yeah, exactly. In PEMDAS, parentheses, you know, so you start with parentheses, there's nothing to do in the parentheses. Exponents, there's no exponents. Multiplication, I do have a multiplication here with the -3. I have a multiplication here with the negative. So in a situation like this, the first thing you do is to distribute. And that comes from PEMDAS itself. PEMDAS tells us to distribute. So now we have 5x plus 9. And what do you know happens whenever you distribute a negative? Yeah, all those signs change. That's just an easy way to think of it. All the signs change. So now I have minus 3x, minus 6. And again, I'm distributing a negative. You could write down a 1 right there if that makes it easier. So you're distributing a negative 1, so again, all the signs change. So that becomes negative 7 plus 4x. Okay, so here we have a long equation with lots of x terms, lots of number terms. What's the next step? Yeah, combine like terms. So that if the first step is distribution, the second step is to combine like terms. So on, per side. So on the left-hand side, I combine my terms to make 2x plus 3. On the right-hand side, there's really no terms to combine, so I just write it down again. All right? So you can only ever combine per side. And folks, can I just show you something real quick? This is a huge common mistake that I see. Every once in a while, I see someone over here on the left-hand side. Okay, there's the equal sign, keep in mind. That's the equal sign. Every once in a while, I see somebody take this negative 3x right here and write plus 3x plus 3x. And then they cancel. What's wrong with that? I mean, what of many, many things is wrong with that? Yeah, instead of doing 5x minus 3x, which should reasonably give you 2x, they actually now added 5x plus 3x to get 8x. Well, we never had 8x's on the left-hand side. On the left-hand side of the equation, you had 5x minus 3x, which is 2x, right? Well, what else is wrong with this? Exactly. We have now added 3x to the left-hand side twice and did nothing at all to the right-hand side. And the basic rule of algebra is you can do anything you want so long as you do it to both sides. And so I see how this looks visually like I just did algebra. I added it twice, but I added it twice to the left-hand side, not once to the right and once to the left. So that happens more frequently than you'd expect. And so let's remember, it has to be one on each side. And furthermore, we don't even have to do algebra yet. We're just combining like terms. So we have 2x plus 3 equals negative 7 plus 4x. Okay, now what? Yeah, we want to put all of our x's to the left and all of our numbers to the right. Or if you're in the mood, you can put all of your x's to the right and all of your numbers to the left. Either way, you want to separate out the x's from the number terms. So we want to move 4x to the left. The only way to move anything is to cancel it. So I write minus 4x, canceled it over there. Algebraically, what I did was legitimate because I did it to the same thing on both sides. And now I have negative 2x plus 3 equals negative 7. So just like I just moved the x's to the left, now I can move my numbers to the right. And I have negative 2x equals negative 10. And then divide out the negative 2. I get x equals 5. One other thing that's a common mistake in algebra, notice what's interesting about this. When you're adding or subtracting, you do the opposite sign. So we went from positive 3, and then we subtracted 3. Those are opposite signs. Every once in a while, I see somebody have a negative 2 being multiplied with x, and then they divide by a positive 2. Do you see why somebody could do that? Because they're constantly thinking you have to change the sign. So then here they change the sign. But that's not correct. Why is that not correct? Wouldn't that be doing the opposite? What? Wait, what's that? Oh, now that'd be a good point. I mean, I suppose you could do that, but even if you did, it would be a negative x and you wouldn't be done yet. So really good point. You can do it if you want to. After all, in algebra, you can do anything you want so long as you do it to both sides. So if you did divide both sides by plus 2, you could, and you'd still be left with that negative 1 there in front of the x. Great point there, Jackie. And then you would get your way finally to the answer of x equals, wait, no. Oh, but that would be a negative 5 and then that'd be positive, yeah. Okay. All right. But ultimately, the reason that here plus turns to minus is because you're doing the opposite, and the opposite of addition is subtraction. But here, what you're doing is multiplying by negative 2, so dividing by negative 2 is the opposite. All right, I'm just going to put back in the right answer. All right, so there we have it. Are we done with the problem? Absolutely not. All we did right now is an algebraic process that generates a possible answer. Remember, just because algebra takes you there, could that answer be extraneous? Yeah, I mean, not in an equation like this, but in a log equation or in a square root equation, any answer you get could be extraneous. So can you ever trust this final answer and just move on? You absolutely can't. You're totally not done with algebra yet. This is just an algorithm that you follow to generate a possible answer, but you still have to go back, plug it in, and see if that answer is even correct, because it could be extraneous, right? Or you could have made a lot of mistakes. So then you go back to the beginning, you plug it all in, and you say, well, 5 times 5 is 25, plus 9, minus 5 plus 2 is 7, minus 21. So that gives me 30, or no, 25 minus 21 is 4, 13 on the left. And then over here, 4 times 5 is 27 minus 20 is negative 13 times negative 1 is 13 on the right. And oh good, 13 on the left, 13 on the right, 13 equals 13. At that point, I'm definitely done. Okay, any questions about the algebraic process? What it looks like? Okay. No, really, does anyone have any questions? I mean, this is a great day for reviewing and wrapping things up and asking philosophical questions. Okay. The second question, I had 2 typos on this practice final. I sent you all an email out yesterday or the day before. Everybody cross out the word width and write blank. Yeah, the question, this statement doesn't make any sense. The width is 20 more than 3 times the width. Is that possible that the width could be 20 more than 3 times itself? What would that even mean for something to be bigger than itself? Is that even possible? Could we even do that? Just for fun, could you even say the width is 20 more than 3 times the width? Is that even possible? It is possible. I mean, just follow the algebra. What do? We move the 3w over, and then we'd have negative 2w equals 20, and then divide by negative 2, and you get a width of negative 10. Now, sure, at this point you'd say, no, that's not possible. A width can't be negative. You can't have a negative number be a width. But watch. If you take negative 10, and then multiply it by 3, and then add 20 to it, what do you get? Yeah. So it is actually possible to take a number and then multiply by 3, add 20 to it, and get that number back again. But not if the number is positive, right? You have to make up a negative number in order to have a situation where something can be equal to 3 times itself plus 20. So yes, while it would be possible to get that number, that's not actually what we want. So did everyone cross out the word length? So the length is 20 more than 3 times the width. Okay, so what is this question asking us to find? Let's start from the beginning. The perimeter of a rectangle is 500. So what's the first thing we should do? Well, I know before we said the first thing you should do is define variables and create equations. But what should you do even before that? Draw a picture. Like, whoa, that should go in step 0. Draw a picture. Even before that, eat a healthy breakfast. All right, so we're going to draw a picture. I've got a rectangle. And the perimeter is 500. How do we, should I just write that off to the right somewhere? P equals 500. What does P equals 500 mean? Yeah, the length all the way around, right? Make up 4 numbers that add up to 500. Just right now. Make up 4 numbers that add up to 500. Where the top and bottom number have to be the same, the left and right number have to be the same. Make up 4 numbers that add up to 500. What's that, Jackie? 100 and 150, so if that was 150, 150, and that was 100, 100, does that work, folks? Would that give me a perimeter of 500? Yeah, 150 and 150 is 300, plus 100 plus 100, that's 500. So, you know, that's a possible rectangle with a perimeter of 500. But they want one where the length is 20 more than 3 times the width. And so right now, if I took this number, 100, and multiplied it by 3, and then added 20, that would give me 320, and that's not 320. So what do I know for sure about this side? Does it have to be bigger than or smaller than 100? Much smaller than 100. Because I need a number that I can triple and add 20 and get that number. So I'd have to have a much smaller number, huh? Let's try a smaller number. What could I try? Why not 50? There. Do those add up to 500? Yeah, they add up to 500. And if I triple it, so triple the 50 and add 20, do I get 200? No, I get 170. So what do I need to do to my guess?
It needs to be between 50 and 60.
Yeah, and I need to choose a number slightly bigger, right? In order to triple it and add 20. Could I just keep doing this until I guess the answer?
Yes.
Yeah, you can just keep doing this until you guess the answer. The thing is, that's not really fun, and it takes a long time, and you never know when you're going to get there. I'm going to try one more. 60. If I triple 60, and then add 20, what would the other numbers have to be? Oh, gosh. If that was 60 and 60, that's 120. And subtracted from 500 is 380. Divided by 2 is 190 each. So that still adds up to 500. And now if I triple it and add 20, that's 200. Slightly too big. So probably a guess of 57, 58, somewhere along those lines. That's what we're looking for. For a number that if you take the length and then make it 3 times, the length is, this length is 20 more than 3 times the width. We'd have to choose a number between 50 and 60. So maybe around 57, that's just a guess. Now folks, was there any value in that activity? Kind of thinking about the problem and trying some numbers and seeing how it works out? Yeah, I think so, because you're just brainstorming the answer. But now, of course, we know we don't have to sit there and guess, we can just do algebra. So what variables will we define? Let's define our variables. Our variables are length and width, right? So I've got length, width, length, width. So we're going to say let L equals length and W equals width. And then we go to the equation, or the very first thing, or the second equation there, it says the length, everybody, I hope you crossed out width there, no length. The length is 20 more than 3 times the width. And most word problems, you translate English directly into math. So when we say the length is always means equals 20 more than 3 times the width. Like the sentence literally translates into English, and it almost normally does. It almost, usually, often case it does. So now I know that L is 20 plus 3W, and L is 20 plus 3W. Okay, then what?
Solve for 500. So you just make an equation for the 500.
Yeah, and go back to your list, okay? With a word problem, we drew a picture, we defined our variables, and we just created an equation, and that equation is that L is 20 plus 3W. But there's a bigger equation that we have to create. And what's the bigger equation we have to create? We still have to use this fact.
Perimeter is 2W plus 2L. So you would set the equation of 500 equals.
Very good. Wait, stop right there. So, folks, perimeter is adding all the sides, right? So if you just did it in terms of the letters, you could say W plus L equals P. Right, that's literally perimeter, adding together all 4 sides. Or you could combine it and say 2W plus 2L equals P. If you wanted to. And then finally, you can substitute in what you had for L, So then you'd have 2W plus 2 times 20 plus 3W equals a perimeter of 500. Now just notice the amount of work we've done, and we haven't solved the problem yet. But we set up the problem, we drew a really nice picture, we created our equation, so we defined our variables, we figured out what L was, and then we created the master equation, like what equation are we talking about, and now we're about to do some algebra and solve and distribute and such. So we get 40 plus W, and combining like terms again, 8W plus 40, and then subtracting out 40, 8W equals 460, and dividing by 8, what would that be?
57.5.
It's what?
57.
Oh, 57.5. There we go. So you get to this answer, and maybe you feel a little uncomfortable about it, and you're like, oh man, it's a decimal, did I do something wrong? Is that the right answer? The only thing to do is to move forward, because we're definitely not done. The question says, find the length and width, and draw a picture. It even told you to draw a picture. So if that's the width, now we have to go back and find the length. So now we're going to take that, plug it into our length equation. L equals 20 plus 3W. So we're going to plug in 20 plus 3 times 57.5, which is 20 plus 172.5. Now again, notice, at this point in the problem, you might have to be pushing through discomfort. Like, oh man, I don't know if this is the right answer. I think this is wrong. There's decimals. But you just have to keep going, get to the next step, and you say, oh, okay, well, apparently that's the length. So I have 57.5 and 192.5. Now what do you do?
You check.
Yeah, the absolute appropriate thing to do at this point, if you were presenting this final answer to someone, like let's say somebody asked you, they're like, okay, I want to build a garden. I need blueprints for a garden. What would be the nice thing to do? To just write down the measurements or actually draw them a picture and label it? Draw a picture and label it, right? I mean, it comes down to whether or not you like the person. If they're an enemy and you're like, it's 57.5 and 192.5, you figure out what to do with those numbers. But if it's someone you like a friend, you'd say, you need a garden that's 192.5 across, and then you need a garden that's 57.5 on the other dimension. And you would hand them that picture, because that's very user-friendly and very kind. Okay, so now do we know yet that we're right? Yeah, we have to actually sit there and plug all those things in, right? So 192.5 times 2 plus 57.5 times 2, and it is a perimeter of 500. Okay, so that would be the last step, and that's when you're done. When you have a really nice drawing that shows your friend the dimensions of the rectangle that you're talking about. If it was not your friend and more of an enemy, maybe you just write down the answer as 57.5 by 192.5. Right, where that x is not multiplication and it's not x, it means dimensions, like width times length or something. But honestly, I mean, look, is that answer as good as the picture? No, the picture's better. The picture is more user-friendly. All right. Any questions or thoughts on that one? I think that was a really nice example of this process. Right? Really nice example of that process. Ultimately, it's not a very hard question, but you do have to, work the process. Okay. Next, number 3. This is my second typo. I sat there and I typed out the completely wrong formula. Did any of you catch that formula is completely wrong? What should profit actually be? What is the actual formula for profit? Revenue minus cost. Now you might say, oh, I don't know, I've never seen that formula before. But you know within yourself that that's what profit is. I mean, if you're running a lemonade stand and you pay $100 to buy sugar and lemons and all that, and then you make $300 in sales, what was your profit? Because you didn't make $300, because you spent $100. So the actual profit would be $200. Your profit is what you made minus what you spent to get it, and so your profit is actually $200. So everybody, please cross out that formula and write down the profit is revenue minus cost. Okay, so we're talking about a business of some sort. We're going to spend money to make money. And let's go ahead and start reading. Assume that the cost to produce an item is a linear function, and all items produced are sold. So that's a lot of information already. Everybody, first look at what they're saying about cost. My cost function, c of x, is a linear function. So that means mx plus b. Right, so my function that represents cost, we're going to call it c of x instead of f of x or g of x. And it's a linear function. And they're also saying that all the items that we produce, we actually sell. So that's good. Like whatever it is you're making, cookies, you're actually going to sell all the cookies as opposed to having a lot of cookies left over and you take it home and you eat it. Okay, the fixed cost is $3,000 and the cost to make each item is $100. Which of those numbers goes where? Which one is the fixed cost and which one is the variable cost? Like if we're making cookies and it's $3,000 is the fixed cost and the cost to make each item is $100. Okay, these are really good cookies. Then which one of these numbers is $100 and which one is $3,000?
3,000.
Yeah, and you know what, folks? There's only 2 possibilities. If you're not sure which one is correct, what could you do? You just try them both, right? And make up a simple example. So let's say that we think the cost function is 100x plus 3,000. Or we're not sure, and so we try it the other way, and we say the cost is 3,000 plus 100. And then you could do something simple and just try. Like try 2 cookies. What do we get? If we do the cost of 2 cookies, then that'd be 100 times 2 plus 3,000. And that would be 3,200. And that makes sense. We're only paying $3,000 once, because that's the fixed cost, and it was 100 for each cookie that we made, so that's 3,200. Whereas if we try this one, and we say, what's the cost of 2 cookies? Well, then that's 3,000 times 2 plus 100. And suddenly, I'm spending the $3,000 twice, and then adding in the cost of 100 only once to get 6,100. Well, that's not a fixed cost if you have to do it more than once, right? So definitely this way is the answer, right? So there's our cost. And again, if you're not sure where to put which number, you can always try both. Okay, so there's our cost. I'm gonna erase some of that. And now they're saying that each item sells for 200. So what would our revenue formula be? Revenue is just the money you bring in. And they're saying that for each cookie that you sell, you're getting 200 bucks. So what would that equation be? What would the equation be to say that for every cookie you sell, you're getting 200 bucks? Now keep in mind, you could do things like you could start pretending. Like, what if you sell no cookies? How much money did you make? None. If you sell one cookie, you just made 200 bucks. If you sell two cookies, you just made 400 bucks. If you sell three cookies, you just made 600 bucks. Right? Because for every cookie, you're getting $200. So what if I sell X cookies? How do I go from the number on the left to the number on the right? What am I doing? You what, Josh?
I can see it.
Oh, okay. What's that? I'm more than doubling it. I am multiplying 3 times 2 is 6, but what else? I'm multiplying by not just 2. Multiplying by 200. So the answer would be 200x. Right? So I want you to look at how I just did that. If you're not sure how to build a formula, make a table of values. And observe the numbers and ask yourself, what am I doing to this number to get that number? What am I doing to this number to get that number? What am I doing to this number to get that number? And hopefully you'll see the pattern and say, hey, I'm taking the input and multiplying it by 200, and therefore, if I have X cookies, my output would be 200X. And so my revenue formula is 200X. And again, once you've generated this potential formula, you would say to yourself, well, let's check it. What if I sold 5 cookies? How much money would I expect to get? If I sold 5 cookies at 200 each, I would expect to get $1,000. And if I plug that into my formula here, my revenue of 5 cookies is indeed 200 times 5, which is $1,000. So that kind of verifies your guess as to what your formula would be. All right, so far, folks, we have built 2 very simplistic models for cost and revenue of my very expensive cookie formula. Could you even imagine a cookie costing $100? What would I have to put in that cookie? Or how big would the cookie have to be to cost $100? Because you know at the grocery store, you can get like one of those big round cookies. How much are those? Yeah, like maybe 10, 15 bucks. If they decorate it with frosting and put your name on it, then it could be 15 or 20. What would a cookie have to be $100 bucks? Like the size of a New York pizza? I don't know. And then just some really fancy ingredients on top, like chocolate fudge truffles. I don't know. Okay, so now what do? We're still reading. Assume the cost to produce an item is linear and that all items are sold. The fixed cost is $3,000. The cost to make each item is $100, and then each item sells for $200. How many items must be made and sold for the company to break even? And how many items must be sold to make a profit? Must be made to make a profit. Well, okay, must be sold. So what do we do now? They're asking about profit. How many items must be made and sold for them to break even? What does it even mean to break even? Yeah, your revenue and your costs are the same. So you spend $100 to make the stuff, and then you earned $100. You're like, dang it, I just wasted my day, right? If you didn't actually make any money, your revenue is equal to your cost. You don't know what to do. So what do we then need to see? We need to see that profit is equal to revenue minus cost. So first of all, we need to just write down the formula. Now, folks, I realize we haven't necessarily spent a lot of time doing business questions like this, but this is not a complex business question, right? They're just saying, pretend you're running your own little mom and pop shop selling something simple. This is the model. And we want to know how many cookies we have to sell to make profit. So what do we do now? We're going to actually plug in what we found out for revenue and cost. So my revenue function was 200x, and then my cost function was 100x plus 3,000. What really important thing do I have to write down right now? Before I start writing down my cost function, what really important thing do I have to write down? That your calculator would need to know. Yeah, parentheses, right? Because we're about to subtract a multi-term expression, which means that that subtraction needs to be, we would need to distribute that subtraction. So very important. So far this is our profit function. We still have to simplify it. Minus 100x, minus 3,000. And that gives us that profit is 100x minus 3,000. So that formula right there is going to tell you your profit. Folks, one of the best things that you can do with any function as soon as you write it down is just throw in some numbers and see if it makes sense. Like, what if I only sold one cookie? How much profit am I going to make? My profit will be negative 2,900. That means I did very terribly, right? If I only sold one cookie, I have that fixed cost of $3,000. I did not recoup my fixed cost, and now I'm in debt $2,900. So that makes sense. Okay, so the question is asking, how many items must be made and sold for the company to break even? Now, what can you do with the function? You can either plug in or set equal to, and what are we saying? We want the profit to be break even, therefore the profit should be equal to 0. Right? That's what we're saying. We're saying, how many would I have to sell to break even? And keep in mind, we're asking, what's my input such that the output would be 0? So how many cookies would I have to make so that my profit was 0, meaning break even? And so now you just do some algebra. Right? So we move that 3,000 over to the other side. 100x equals 3,000. Divide by 100. And x is 30. So 30 cookies will get you to break even.
With these, you just set profit equal to the revenue equal to cost.
No, you can do that too. You can do that too. Breaking even means they're equal, right? Thank you, Abe. Great question. If you want to ask specifically break even, you can also just say that means revenue must be equal to cost. Does that make sense? That breaking even means your revenue is equal to your cost? So you can do that by all means. You could set that now equal to 200x, equal to 100x, minus 3,000. And then you move that 100x over. Really good question, Abe. So now notice, wait a minute.
Plus 3,000. You have the original that you had.
Oh yeah, the original equation. Thank you. Yeah, the original revenue, the original cost. Okay, that makes more sense. So then, yeah, when you divide off the 100, you do get x equals 30 as well. Hey, by all means, if you'd like to do it that way, you can. Breaking even means revenue equals cost. Yeah, you can do that. However, the next question they're asking, although you can still do it this way, is how many items must be sold to make a profit? So what does that mean we're saying now? What do we want our profit to be? If we actually want to make a profit, what question are we asking? I want this profit, I want to make profit, so I want this number to be positive. What positive number? Any positive number. So what do I write? Yeah, greater than or equal to 0. That's what actually greater than or equal to? Just greater than. Yeah, I want to know greater than, right? So now I solve the exact same algebra, which I didn't have to erase all that, I could just change the algebraic sign, but 100x has to be greater than 3,000. And so we divide by 100, and then we get x is greater than 30. Now what does that mean, x is greater than 30? If I make a number line and I go to 30, and I shade to the right, is 30.5 an answer? It says the cost to produce an item. Can I sell 0.5 of an item? Yeah, I mean, it really depends on if you're allowed to sell parts of something. Like if you're Costco and you're selling pizzas, they do sell pizza by the slice, so maybe you could sell 0.2 of a pizza. But if you're selling cars or cookies or things that come as an item, then how many items do you have to sell to make a profit? The answer would be 31 or more. Right? Because we wouldn't allow decimals or fractions. And now going back to Abe's idea, if we wanted to make a profit, what does that mean, Abe, about your revenue compared to your cost? It's no longer equal to. You want to make a profit. Yeah, you're looking for when is revenue greater than cost. And yeah, by all means, you can solve it that way. So then you'd have 200x must be greater than 100x plus 3,000. And then you do the same algebra, and you get 100x must be greater than 3,000. Or in other words, that x must be greater than 30. Which again, if it's solid items like cars, you couldn't sell 30.2 cars, you say 31 cars or more. Okay. Well, folks, really nice. I feel like we're really covering this in depth. We're really talking about it very well, at a high level, understanding what we're doing. Let's go ahead and take our break now. Let's see here. Oh, 9 to 5, let's come back at 9:15. Good question. Yeah. Oh, there's no notes. Okay, we set it right up on my desk right now. All right, folks, let's keep going. So, number 4, we have got 2 functions and we want to find compositions. This is not that long ago that we were doing this. So those first 3 questions were more like basic algebra questions in general, whereas number 4, this is coming from chapter 5. So how do we solve these 2 problems? They're interesting because they reflect different processes, right? So on the one hand, we have f of g of x, where we're plugging x in. But then on the other hand, we have g of f of 3, where we're plugging 3 in. So let's start with this one. How do you plug a function into a function? What's the first thing you write down? Yeah, in this case, you write down the first function first, the outside function. You do the outside function first, which is f. So the structure of f is something squared plus 3. That's interesting to note that when you're plugging x into a composite function, you start by writing down the outside function first as the large structure. And then what do you plug into it? G of x, which is 5x minus 2. So notice that when you're doing a composition where x is being plugged in, which means you're not really plugging in anything, you're just making a formula, you first do the outside, and then you plug in the function on the inside. You're not really doing anything with x per se, you're just plugging the g function into the f function. And now at this point, that's the correct answer. But should we simplify it? You should simplify it. Because you never know if simplifying it will lead to some better simplification. So let's just go into it real quick. If we simplify that, we're going to FOIL. You can FOIL scratch work on the side there. I'm just going to write it down. 25x squared minus 10x plus 4, and then plus 3. And then that gives us 25x squared minus 10x plus 7. So that would be the answer to the composite function, f of g of x is 25x squared minus 10x
It's
plus
minus
7.
20.
What?
It's minus 20.
Oh, so it is. Thank you. Minus 20x. Sorry, folks, I did that. See, I should have done my FOIL work on scratch work, so I didn't make a mistake. Okay. So we work from the outside in. We work from left to right. That's the big thing to notice. Whereas now, if I'm doing g of f of 3, where do we work?
Solve for f of 3.
Yeah, now we work from the inside out. We first say, well, I'm plugging 3 into the f function. So if you want to, you could go somewhere else, scratch work, and just take your f function, and then plug in 3. So f of equals something squared plus 3. I'm going to plug in 3. So f of 3 is 9 plus 3, which is 12. So right now what I'm going to do is I plug 3 into f. So this whole thing, f of 3, is replaced with what f of 3 is, which is the answer, yeah, 12. Oops. Yeah, so now I have g of 12. I'm working now from the inside out. And now I have g of 12, so once again, you can just go off, get some scratch work, and plug 12 in the g function. So now I have g of x is 5x minus 2, so g of something equals 5 something minus 2, which we're plugging in 12. So that gives us 60 minus 2, which is 58. So now that whole thing is 58. Now that's simply one way of doing it, right? Do you have to do it that way? You certainly don't. You could approach this problem the same way you did the first problem. And you could just go ahead and find g of f of 3. I'm sorry, g of f of x. If you wanted to find that first, you'd write down the structure of g, which is 5 something minus 2. And then plug f into it, which is x squared plus 3. And then distribute and simplify, so you have 5x squared plus 15 minus 2, which is 5x squared plus 13. And now that I know that g of f of x is 5x squared plus 13, I can take that formula and plug in 3. Right? That should give me the same answer, if that's how you want to do it. And sure enough, 3 squared is 9, times 5 is 45, and 45 plus 13 is 58. Whichever process you do, you'll get full credit. That is, whichever of those two processes you do, you get full credit. Is there a third way to do the problem? I don't think so. I think you either choose one of those. Questions about it? Okay, and number 5, it says find all solutions to the equation that give you a quadratic. What are 7 ways that we can solve this problem? 7 is a joke. That's like higher than what we probably have. Well, we probably have 3 ways to solve this problem. You could try to factor it, right? So I'm just going to start by writing down 3x squared plus 6x minus 13. And the first thing we could do is try to factor it. What's the next thing we could do? We could do the quadratic formula. That'd be the easiest. Probably, because factoring might be hard. Or we could graph it, because you know that the x-intercepts are going to be the solution. Now, as far as which one of these 3, the instructions don't specify. It just says find all the solutions. Now, again, imagine, depending on what the graph is either 2 solutions, or 1 solution, or no solutions. So if the answer was no solution, you'd have to write no solutions. Like there are no values for x that would make that thing true. Although you know that's not true, that simply means the solutions are imaginary, right? So you would still have solutions to give. It's still a solution just because it's not an x-intercept. So you would say no real solutions, but you would have some sort of answer in terms of I. Okay, so then what would be easiest? Probably the quadratic formula, because you can just say a is 3, b is 6, c is negative 13. Now, I already have this solution written down on the solution guide that I posted on Canvas, so I don't think I'll do the quadratic solution, but instead, just in case anyone wants to see it, how would we do the factoring method? Now, keep in mind, is every quadratic factorable? No. So you might even try it, it doesn't work. Like right here, I'm going to say 3 times, so because there's a number on the x squared, you multiply. 3 times negative 13 is negative 39. And you say, what can I multiply to make negative 39 that adds to make 6? So it's either 1 times 39 or 3 times 13, and that's it. Do either of those add up or subtract to make 6? No. So you can't even factor this one, because nothing multiplies to make 39 that would add to make 6. So this one's not even factorable. So you would just be left with doing the quadratic formula or graphing. Now for the quadratic formula, you do have to memorize that. They don't give it to you on the test, so negative b plus or minus the square root of b squared minus 4ac over 2a. Probably the biggest mistake I see is that people don't square that b. Now if you don't have this formula memorized, what could you do? What's that, Josh?
Sing the song.
You could sing a song, or you could just write it down 20 times. Right? Like if you just go home and sit down and write it down 20 times, I'm pretty sure you're going to memorize it. If not consciously, then physically, your hand will remember what to write. Yeah, Chelsea?
I'm thinking, I got one of the same solution.
Uh-huh.
But not.
Oh, well, maybe I made a mistake. Let's check, folks. So I'm going to write it down empty. So negative b plus or minus the square root of b squared minus 4ac all over 2a. And folks, when you're sitting at home writing this formula down, say it as you write it. That's very important. You memorize things that you say and write simultaneously. So b, b, a, c, a.
One of your formulas is over 6 and one of them is over 3, so I think it's just a typo.
Maybe I bet I did do a typo then. Let's see. So we've got,
Even then, my decimals aren't the same as yours.
well, that looks like I did make a mistake. So far I have this, and then negative 6 plus or minus the square root of 192. Is that correct so far?
Yeah.
Okay. And 192 is divisible by 16?
64.
Oh, 64. So folks, as a separate question, you have to be able to simplify root 192. That would be best anyway, to simplify root 192. So you'd have to say what square number goes into 192, and you'd have to sit there and look at all your square numbers, 196, 149, 16, 25, 36, 49, and on until you find one that goes into it, which happens to be 64. So 64 times 3, which is root 64 times root 3, which is 8 root 3. And so that gives us negative 6 plus or minus 8 root 3 all over 6. And then at that point, the whole numbers can be simplified against each other. So 6, 8, and 6 are all even, so you can divide them all by 2. So that's 3, that's 4, that's 3. And you get negative 3 plus or minus 4 root 3 all over 3. Yeah, I must have made a typo there.
But so, am I plugging it in incorrectly then? Because if I'm solving for it, I'm doing parentheses negative 3 plus 4 root 3 and parentheses divided by 3.
Yeah.
But neither of my answers match your answers.
Well, let's look. Negative 3 plus 4 root 3, parenthesis, divided by 3. There's one answer. I did the plus 1, which is 1.3094. And then if I change that to minus, negative 3 minus, I get negative 3.3094.
Okay, so our answers do match here. They just don't match on the key.
Oh, man, so my key doesn't. Well, now how do we check anyway?
Plug it in.
Yeah, see, you still have your calculator method that you could do. So you can do 3x squared plus 6x minus 13. And there's my quadratic. And the answers are negative 3.309 and 1.309. Yep, and that's what the answers were. So definitely on a problem like this, use your calculator to get a decimal approximation. But keep in mind that the answer I want to see is this. Now, this is also the answer. If you gave the answer negative 6 plus or minus root 192 over 6, I'd probably just take off 1 point for not doing the additional skill of simplifying the root. But doing the additional skill of simplifying the root is part of normal mathematical procedure. You always simplify roots just like you always simplify fractions. You know, if you left the final answer to me as 10/20ths, it's accurate, but it's not simplified. You know, I would take off a fraction of a point for not simplifying your fractions. I would take off a fraction of a point for not simplifying a root. So that's our answer, but the decimal answers are these, and that's what you can check on your graph. Now, folks, ideally you're showing this process because to get full credit, you need this answer. Because that's the exact answer. If what you did is just did a graph, and you looked at it on your calculator, and you saw that the graph looked like this, and you wrote down 1.3094, and, sorry, no, 1.3094, and negative 3.394. If you just gave that answer, I would still take off some points, right? Because those answers are not exact. The exact answer is negative 3 plus or minus 4 root 3 over 3. These are just decimal approximations. So they're not the actual solution. And why do I say that? Like, do you think I'm being very unreasonable right now? Like, oh, Mr. G, what's up? Like, I graphed it. There's the numbers. Well, what's the solution? I erased it. What's a solution to an equation? A number you can plug in to make the equation true. If you plug that number into this, it's not going to be true. If you plug that number into this, it's not going to be true. It's going to be really close. It's going to be like 0.03 equals 0. But is 0.03 equals 0? No. So these are not the answers. Those are decimal approximations to the answer, but they're not the solution. This is the solution. So when the instructions say find the solution, that means find a number that you can plug into the equation that makes it true. And 3.309 is not a number that plugs in to make this equation true. It's merely a decimal approximation of the solution. Does that make sense? Do you think I'm being like, geez, Mr. G, you're so mean? I mean, I'm just being exact. Yes, Josh?
So you want us to write our answers with negative 3 plus minus 4?
Right, this would be the best answer for full credit. This would be an unsimplified answer for partial credit. And this would be a decimal approximation for partial credit.
Would you want to just x negative 3 plus minus or like x negative 3?
Oh, either way. I mean, if you actually wrote out negative 3 plus 4 root 3 over 3, and then you also wrote negative 3 minus 4 root 3 over 3, I think that's unnecessary. I think mathematicians are all pretty happy with that answer because it's more concise. Yeah. All right, wonderful. There we go. So what is that question really testing? Your ability to do the quadratic formula. And by all means, check your answer with your graphing calculator, but don't just use your graphing calculator. All right, the next one, solve the inequality. Now this is a fun one. I don't recall off the top of my head, I think we did a compound inequality of this sort, where you have two inequalities at the same time. Did we do one of those? I think we did. In any case, it's just like any other inequality, except for the fact you have two of them. So it says solve the inequality. Now again, if there's like one thing that you leave this class with, it'd be the ability to answer my question. What does it mean to solve this inequality? To find numbers that you can plug in to make it true, right? Like that's the biggest level idea from all of algebra. We're looking for numbers I can plug into this thing to make it true. So let's, if I just randomly tried a number like 1, and I plug 1 in, 8 minus 5 is 3. 3 is less than 5, and it is greater than negative 10. So yeah, x equals 1. X equals 1 is one solution. I just found one. But how many solutions are there? Infinitely many solutions. So just saying, like, if you were like x equals 1, yeah, that's true. That number will plug in and make it true. But it's not all the solutions, right? We want all the solutions. So all the solutions we get by actually solving. So what's happening to x? It's being multiplied by negative 5 and then added by it, because the sign in front of the 8 is positive. So, and plus, if you really want to see that better, you could always rewrite this as negative 5x plus 8. Then it's even more obvious that x is being multiplied by negative 5 and adding 8. So now we go through the process of subtracting 8. So we have negative 3 greater than negative 5x, negative 18. Yeah, this is really a tricky one. This is why they put this on tests, to make sure that you look at the sign in front of the number to say what that number is. So like this 8 is definitely positive and that 5 is definitely negative, and by rewriting it this way, this 5 is still negative and this 8 is still positive, and therefore that was a legitimate thing to do. And plus it makes it easier to see that x is being multiplied by negative 5 and then being added by 8. Okay, so now x is being multiplied by negative 5, and we're about to divide everything by negative 5. What does that mean we have to do?
Change the signs.
We have to change the symbols, these inequality symbols. So now it's going to be less than or equal to, and that becomes x. And over here we have 3/5, and over here we have 18/5. Now those fractions are simplified, but since these fractions have finite decimal representations, I think that would be easier on your audience. I think somebody at Home Depot, or if you're ordering a pizza, they would far prefer that you actually say x is less than or equal to 3.6 or greater than 0.6. Like, wouldn't that be a better answer than 18/5 and 3/5? Again, if you're thinking about your audience and you're thinking about who you're giving these numbers to, since it's a finite decimal, that looks better. Because everybody understands $3.60 and 60 cents. But if you walk up to somebody and you're like 18/5, like you just put them into a partial coma for a couple seconds, right?
Is it only when you're dividing, is that you're changing the symbol?
Is it what?
When you're dividing, is that the only time you're changing the symbol?
If you multiply or divide by a negative.
Okay.
Yeah, anytime you multiply or divide by a negative. Okay, so now what does this look like? We draw our number line. We have a 3.6 here. We have a 0.6 here. We have what kind of circle for this one? Yeah, filled in, shaded, closed. And what kind of circle over here? Open. And then we shade everywhere in between. X is literally in between those two numbers. So you're shading in between those two numbers. And then in interval notation, we have our final answer of 0.6 to 3.6. You'll notice my original guess, x equals 1, is on that interval. I originally guessed, okay, let's try 1, and sure enough, 1 was a number that made the inequality true, but so is any number between 0.6 and including 3.6. The instructions say express your answer in interval notation and graph the solution on a number line. Honestly, all three solutions go hand in hand. All three should always be done. If you're giving an answer to some sort of inequality, give all three. See how they all work together. Okay. Return the page, number 7. Find the solution to the inequality. Make a graph of the situation and express your answer in interval notation. So, first of all, what's different about this problem? Or what makes it a little tricky? Yeah, it's quadratic, so it's a parallel, but the inequality, the greater than. So what does the greater than mean we're looking for? Where is the graph? Yeah, above the x-axis. Right? Because it says greater than, we're looking for when the parabola is above the x-axis. Now again, folks, you have a graphing calculator. You can graph this on your calculator and get all the information right out of your graphing calculator. So, the very first thing you can do with your graphing calculator is just type it in, x squared minus 8x minus 20. You can look at that parabola and steal all that information. You can say, hey, -2 and 10. And it goes down quite a bit. So everybody might as well graph that graph between -2 and 10. Now looking at your graphing calculator, you know it goes between -2 and 10. So what do we need then? Notice there's no axis. They expect you to draw in your own axis to fit the graph on the graph. So since we're going between -2 and 10, let's just say I'm going to put the -2 over here and the 10 over here. Then my axis probably is going to be somewhere in here. So maybe that's going to be my y-axis. And then maybe I put my x-axis up here. And now I need to count something out. If I go -2, 1, 2, do I have enough? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, good idea. So here's my -2. And here's my 10. Again, you just have to fit it onto your graph. Isaac, Josh, did you guys have a question? Okay.
Solutions are on the,
On the previous one?
yeah.
Was it different?
No, I was just telling that it's online if you didn't get it.
Oh, okay. Yeah, it's posted on Canvas. All right, so now just again looking at your graphing calculator. Oh my. The chair I just happened to pull is missing a wheel. That was probably going to be the first time ever that I was going to fall off of the chair. Wow. Here, I shouldn't put it back because now I'm going to put it here. That way no one is going to, well, other than me tripping on it. Okay. So we want to draw a parabola. It's not asking you to make an incredibly detailed graph. In this particular case, if we wanted to, we could just go ahead and draw our parabola. Right? No need to be overly specific. It doesn't say to make sure you're marking the y-intercepts and the x. We just need a graph. So there's our parabola, and we're asking again, greater than 0 means above the x-axis. So we can already see where that is. It's going this way and this way. Now, are we saying greater than or equal to the x-axis or just above the x-axis? Is it greater than or equal to the x-axis or just greater than the x-axis? Just greater than. So what kind of circle should I have here? Yeah, those are open circles. That's a good detail to include. And therefore, our answer is, what values are we talking about? Anything to the left of -2 and anything to the right of 10. So first you want to make a number line to convince yourself of what this answer is going to look like. It's a -infinity, or from 10 to positive infinity. And then you can actually put in your interval notation of -infinity to -2, union 10 to infinity. Now, what we just did is a perfectly legit answer to the question. It says to find the solution, make a graph, and express your answer in interval notation. So we did all that. But just to remind you, let's say the graphing calculator gave you a decimal. You couldn't give that decimal as the answer unless it's a finite decimal, because then you're not really giving the exact answer. You'd need the real answer. So you would either have to do the quadratic formula, that would give you the exact answer, or remember that you can also factor. You can say, if I want to find the x-intercepts, you pretend the x squared minus 8x minus 20 is equal to 0, just for the moment. You say, hey, I want to find the x-intercepts. And the x-intercepts are when the equation is equal to 0. Because then I can factor and say 1 multiplies to make 20, that adds to make 8, which is x minus 10 and x plus 2. Which, by the zero product rule, gives me x equals 10 and x equals -2, which is the exact same answers you got from your graph. So the best answer would include either factoring or quadratic formula to show where you got the numbers -2 and 10 from, but your graphing calculator does show you that. So what does this problem mean? Let's say I take any number right of 10, like 12. What should happen if I plug 12 into that quadratic? My answer should be, if I take any number over here, like 12, and plug it into that quadratic, my answer should be true. Wait, what else? The answer will be true, but more importantly, that number will be greater than 0, meaning positive. Right? That's really what the problem is saying. It's saying, how do I get a positive number out of that function? if that's a function, input, output, what input do I have to give so that the output is positive? Greater than 0 means positive. So if I choose any number over here, plug it in, I'll get a positive output. I take any number over here, plug it in, I'll get a positive output. That's really what we're saying is we want the function to generate a positive output. Okay, moving on, inverses. We also did that in chapter 5, I think. So we'd like the inverse of this function. Now recall, what does inverse even mean? If I'm looking at the original function and I plug in, I'd like to plug in, let's plug in 1. So if I plug in 1, then that would give me 8 over 5. So that's the original function. What were you going to say, Josh? Well, yeah, that's to do the actual process of finding the inverse. I'm just saying, what is an inverse? So in this function, 3x plus 5 over x plus 4, if I input 1, I output 8/5. So what's an inverse function?
The inverse function is changing and swapping.
Yeah, the inverse function, f to the negative 1 of x, would be some other function that I'm going to write down eventually, f inverse of x. And whatever that function is, it better have the property that if I plug in 8/5, what will it equal? 1. So that's what an inverse function does. It swaps the role of input-output. And that's what the inverse function will be. Some function that if I plug in 8/5, it should equal 1. But more importantly, if I plug in any input and output over here, I should be able to plug the output into the input, and it will give me the output, which is the original input. Okay, so what do we do? Remember that it was a multi-step process where you start by writing down f of x. Now, it's going to take a lot of space here. You start by writing down f of x equals 3x plus 5 over x plus 4. And then you replace f of x with y, just to get out of function notation and into 2 variable notation. And then you replace, yeah, every x becomes a y and every y becomes an x. So now we have x equals 3y plus 5 over y plus 4. This is a really great example of algebra. You know, like number 1 was a fine example of algebra. But this is a fun example of algebra because we're presented with a problem, which is the denominator. How do you get rid of a denominator? Yeah, multiply off the denominator. How do you get rid of a denominator? You cancel it, you destroy it. So by multiplying both sides, I destroy that denominator, and now I no longer have that denominator. My life goes back to being convenient. So now over here, I'm going to distribute my x and get xy plus 4x. Over here, I just have 3y plus 5. And now, at the very least, I don't have a denominator. I still have lots of terms. And what's my goal anyway? What's my goal? I swapped out x and y, but my goal is to get y by itself again. So it's like we have y by itself, we're like, whew, there's y by itself. And then we buried the y term into the expression, and we have to dig y out and get y by itself again. So how do I get y by itself? I want all my y terms on the left and all my non-y terms on the right. You know, normally we're putting the x terms to the left and the number terms to the right. Right now we're bringing the y terms to the left and the non-y terms to the right. So I bring my 3y over here to the left to get xy minus 3y plus 4x equals 5. And then I want to move my non-y terms over to the right, which is my 4x, so I can move my 4x over to the right. And now I have, before I write this again, what can I do with the xy minus 3y? Yeah, factor out a y. So now this is really y outside of x minus 3 equals 5 minus 4x. And now I essentially have y by itself. I have a single y variable. It's sitting there in front of the x minus 3. So y is being multiplied by x minus 3. So I divide by x minus 3. And I get y equals 5 minus 4x over x minus 3. Now let's say you're taking this test, and you really want to make sure you get this answer right. What do you do now? Do you close your eyes and pray? Gosh, I hope I got that right. Or how do you know that you got it right? Yeah, I mean, you could try that test value. You can plug in 8/5 and see if it works. Right? 8/5 isn't that terrible. That's 1.6. I can use my calculator, plug 1.6 into that, and see if it actually generates a 1. So that's one thought. I could actually do a test value. A test value is a fairly good way to check to see if you got the right answer for an inverse. So if I do parenthesis 5 minus 4 times 1.6 parenthesis divided by 1.6 minus 3, I get 1. So yeah, at least for my one test point out of infinitely many test points, It worked. So that gives me some confidence. What will give me even more confidence? How do I know if this thing really is the inverse?
And then can see if you can graph both equations and see if they mirror.
Yeah, exactly. Remember, if you graph both equations on your graphing calculator, they should be mirror images of each other across the diagonal line y equals x. So you can always take your graphing calculator and do the first one, 3x plus 5 divided by x plus 4. And then you graph the second one, which is 5 minus 4x divided by x minus 3. Is that it? Yeah, and I mean, as soon as you look in your graphing calculator, it should be immediately apparent to you if it's symmetric. Like, just look at that. Can you tell that it's symmetric? Like, again, just turn your head at a 45-degree angle, and is it symmetric? It should be immediately obvious to you that you have the right answer. Because if I even change one little thing, like that minus 3 becomes a plus 3, well, I mean, that's already different. There. Is that symmetric? No. That's not symmetric across the diagonal line y equals x. You can even graph the line y equals x. And to make it even more obvious, and look at it and say, do I see the same thing on the left as I do on the right? No. So, by all means, folks, you can check your answer on the test. Okay. Questions about that inverse process? A word about inverses. You might look at inverses and be like, that's a weird skill. Why would I ever have to know that skill? That's weird. Who cares? But see, inverses allow you to ask questions in reverse. So like, if I said, you know, I'll just say verbally, I won't write it down. How many hours do I have to work to make 20 bucks? That's one question. But then I could say, oh wait, how many hours do I have to work to make 20 bucks? On the other hand, I could say, how much money would I make if I worked 5 hours? So those are two opposite questions, and they're just treating the input and output oppositely. And that's why an inverse would be helpful, to be able to ask a question in the reverse order of input output. Okay, graph the function, give the coordinate. Oh, this one you got to do it all. Graph the function, graph the coordinates, the vertex, the y-intercept, the x-intercept, domain, range. Whew, this is a great problem. What's the first thing you could do? Graph it, right? You all have graphing calculators, at least you should. And during the test, I'll bring extra graphing calculators. And I'm even a really nice guy. I'll even help you use your graphing calculator. So we just type in our graphing calculator, this whole thing here, and we get this. Like I said, you can use your graphing calculator during the test, so you could use that to support your answer. So looking at this, where do we want to draw our graph? Or that is, where do we want to draw our x-y axis? Because your graph is blank. So what do we need? We need to draw the x-axis to the right and the y-axis toward the bottom, maybe, so that we can fit in all these points. Yeah, those are all the points that we need. So we need to go up 4, down 5, and we need to be able to go left 5 at least. So let's see, can I do both of these? No. Move that over, shrink it down. Okay. Oh, oops. Oh, that doesn't help at all. Oh my gosh. All right, I give up. So, what do we want to graph then? On our graph, we would need to put maybe our x-axis off to the right a little bit. And since our graph needs to go down to the y-intercept more than it has to go up, I'll put my y-axis up a little bit. So you see how I did that? I moved my x-y axis off to the side so that I could actually see where all my points are. So now I can plot in my x-intercept at -1, another x-intercept at -5, 2, 3, 4, 5. I've got my vertex up at -3, 4. So that's -3, and that's 1, 2, 3, 4. And then I had a y-intercept down at 1, 2, 3, 4, 5. And now I can sketch my graph. So it did say graph the function. I completely just used my graphing calculator to do that. Now keep in mind though, you could get all this information from the paper. Because we have g of x equals negative x plus 3 squared, what, plus 4? So what does that information mean? Our vertex got moved which way, left or right? Left 3 and then up 4. So remember, outside is vertical, which is the same sign, so plus 4 means up 4. Inside is horizontal, which is the opposite, so plus 3 really means left 3. So my vertex, therefore, is left 3 up 4. Left 3 up 4. You can read the vertex right from the equation, or you can look at your graphing calculator. That's the vertex. What's the y-intercept? Now you have to write all this stuff down. You know, it's on the graph, but write it down. The y-intercept is negative 5. And how else could we have found the y-intercept? Going back to the original question on my warm-up here, how do you find the y-intercept? You plug in 0, you plug in 0. So if I plug 0 to this, 0 plus 3 is 3, 3 squared is 9, negative 9 plus 4 is negative 5. So there's my y-intercept. What are my x-intercepts? I just found those by using my graphing calculator, negative 5, negative 3. And now they want the domain and range. So recall the definition of domain and range. Domain is how far the graph goes. What? Left to right? Yeah, left to right. So domain is left to right, whereas range is how far the graph goes down to up. So remember, it's left to right, down to up. So how far left and right will this graph go? How far left will it go? How far right will it go? To infinity. So my domain is negative infinity to infinity. Whereas my domain, how far down does the graph go? I'm sorry, range. How far down does it go? Infinity? Negative infinity? How far up does the graph go? To 4. So my range would be down from negative infinity up to 4. Sorry, infinity is always in parentheses. There we go.
So for y-intercept and x-intercept, you want us to do that plugging in?
Well, you know, the instructions don't specifically state how to find all this information, but certainly you can find the y-intercept by plugging it in, and you find the x-intercept by setting it equal to, right? So if you wanted to set up some work and said y-intercept is g of 0, which is negative 0 plus 3 squared plus 4, which is negative 5, and then the x-intercept is pretty simple. You set g of x, which is negative x plus 3 squared plus 4 equal to 0, and you can all solve this. It's just basic algebra. You say x is being added by 3 squared multiplied by negative 1 and added 4. So you subtract the 4. Then you have negative x plus 3 squared equals negative 4. So it's being multiplied by negative 1. What can I do besides dividing off the negative 1 right now?
I'm sorry, isn't the y-intercept positive 4?
No, the y-intercept is down here.
Oh,
Negative 1. Yeah. What can I do besides dividing off the negative 1? Remember, we learned a trick for changing the signs of everything. Instead of dividing off this negative 1, I could just multiply both sides by negative 1. And that just changes the signs both positive. So that's done. So now x plus 3 is being squared. I would square root both sides. And get x plus 3 is equal to plus or minus 2. Now this will become interesting. Now to solve for x, I subtract the 3. And what I get is x equals negative 3 plus or minus 2. Now what is that? On the one hand, you have negative 3 plus 2, which is negative 1. And you have negative 3 minus 2, which is negative 5. Which is indeed your two x-intercepts of negative 1 and negative 5. Now again, you can read all that stuff off the graph, but you can also do it manually. Using the knowledge that you all have, that to find the y-intercept, you plug 0 in, and to find the x-intercept, you set the function equal to 0. Okay. The next question says, write the equation of the line that passes through these two coordinates and put your answer in slope-intercept form, y equals mx plus b. So what would you do here? You want a line that goes through those 2 points.
Do this slope formula, which is y2 minus
You want to find the slope. What else would be a good thing to do first? Sure, label our coordinates. What else would be a good thing to do first? Yeah, I would graph it, folks. I would give your brain something visual to hold on to. If you don't mind, let's move this up. I would give your brain something visual to hold on to and actually graph the 2 points and actually draw a line through them and just see what the equation looks like it's going to be. So I'm not saying every problem like this will be this easy to solve, but just for fun, if you draw a graph and you put in 2, 1, 2, 3, 4, and you put in -2, 2, and draw a line. I mean, if we were just sheer dumb lucky, what y-intercept does it look like? It looks like a y-intercept of 3. And furthermore, what does the slope look like? Yeah, up 1, right 2. So just based on the graph, just boom, I just plotted 2 points, I drew a line, I was like, hey, if I'm lucky, it's going through that number 3, then my equation, y equals mx plus b, is a slope of up 1, right 2, plus 3. Right, so that's just by making a sketch, which is a really good idea because it gives your brain the actual concrete knowledge of what on earth this problem is about. This problem just says, find a line that goes to those 2 points. So you plot the points, you draw a line through it, you look at it, you say, what's the y-intercept, what's the slope, and you write it down. That's the answer, by the way. But let's just say that you wanted to go at it a longer way. Of course, like if it wasn't so obvious, like if you're like, uh-oh, it doesn't look like it's cutting through exactly an integer, then of course you'd have to do the slope formula. So m equals y2 minus y1 over x2 minus x1. And you'd have to label, so this is my first coordinate, x1, y1, my second coordinate, x2, y2. And then you go about plugging everything in to your formula. So my y2 is 2, my y1 is 4, my x2 is -2, my x1 is 2. And that gives me -2 over -4, which simplifies to 1/2. So now I know my slope is 1/2, which you'll notice is the same slope I got from the graph. So then now how do you solve for the y-intercept? You solve for y-intercept. Any thoughts? How to go about it? Because keep in mind, what are we trying to solve for? We want y equals mx plus b, which means we have to solve for m, we have to solve for b. And so far we have that. So how do we find b?
Y minus y1.
Oh, you do point slope form?
Yeah.
Sure, you can do point slope form. So point slope form is y minus y naught equals m times x minus x naught, where y naught and x naught are any coordinate. So I'm just going to now relabel one of my coordinates as x naught, y naught. And I can write in y minus y naught equals m times x minus x naught, where my m is what I said, 1/2. And my y naught is 4, and my x naught is 2. And now I have the equation, right? If you memorize point slope form, all I have to do now is simplify. So I distribute my 1/2 as 1/2 x minus 1, because half 2 is 1, and then add 4 over. And I get y equals 1/2 x plus 3. So that's another way to do it. What would be a final way to do it? Like maybe you don't want to memorize point slope form. Look at the equation y equals mx plus b. What do I know? Well, what do I not know? I don't know b. Do I know m? Yeah. Do I know a value for x and y? Sure, either of those. I'm going to choose my 2, 4 again. I can put in a 4 for y and a 2 for x. Now can I solve for b? Yeah. Because half of 2 is 1, so 4 equals 1 plus b. And then subtracting off the 1, b equals 3. Did anyone like that last approach?
Yeah.
I mean, all 3 of those approaches are great. Now again, you have 3 ways to solve this problem on the final. Which method should you use? All 3, right? Always the answer is use as many methods as you have. Like if you have an untimed test, which my tests are essentially untimed because I let you work longer if you want it, you might as well use more than one method. All right. Oh boy, we're back to synthetic division, what I think is everyone's favorite section, synthetic division. It says, find all the roots of the polynomial given that x equals -4 is a root. Now folks, what should you do as soon as you see this, cubic formula? What should you do to find all the roots? I don't mean to shit all over you. Have you ever heard that phrase? You're shitting all over me. Don't shit all over me. What should you do as soon as you see that? You what?
You plug in negative.
Well, sure, you could do synthetic division with -4, but even first it says find all the roots. What does root mean? Solutions, which also means all the zeros, which also means, I think someone already said it. Well, that's true, the numbers you can plug in to make it true. The x-intercepts, right? Root, 0, solution, they all mean x-intercept. So if I were you, I would just immediately take out my graphing calculator and graph it. So I've got x cubed minus 2x squared minus 19x plus 20. And Whammo, I've got a graph. I can find my 3 x-intercepts, -4, 1, and 5. So everybody, make a graph. It's going to squiggle up, then down, and then up again. And it's going through -4, 1, and 5. This is not cheating. This is your graphing calculator, immediately telling you the answer. Now, of course, you still have to show some work. Because that's, part of the problem is to demonstrate your knowledge of synthetic division and such. But at the very least, what were they again? -4, 1, and 5? Okay, great. At the very least, if that's all you did for this whole problem, that's all you did was just write that down, you get some points, right? Now, it says find all the roots of the polynomial. I just did, because roots are x-intercepts. Given that -4 is a root, what they want us to do here is synthetic division. And I'm telling you right now, that's the specific instruction. You need to show work, you need to show synthetic division work to get your full credit. So we'll do -4 plugged into 1, -2, -19, and 20. And recall the fun of synthetic division. You drop the first one, and then multiply, add, multiply, add, multiply, add. And you all remember why it's so exciting that it ends in a 0? Yeah, there's no remainder. It means -4 is a x-intercept. Yeah, it is true, and it is a correct answer, but it's an x-intercept. And recall what synthetic division is. It's a machine that does input-output. This is input-output. This is the same as if I had just done P of -4, plugged -4 into all that, and got 0. So input-output, that means the coordinate, -4 is 0, is on my graph, which means -4 0 is an x-intercept. Okay, so then what? I'm going to erase that because it's kind of in my way. But yeah, synthetic division is an input-output machine. So now we bring down this and this, and we write down our factored polynomial. So if -4 is the actual x-intercept, and -4 is the number you plug into synthetic division, what is the factor that represents? X plus 4. Remember, you only change the sign when putting it into factored form. -4 is the x-intercept on the graph. It is the number you're inputting. But as a factor, it's x plus 4. And then the other part, since we started as a cubic, it's 1x squared minus 6x plus 5. So now we have x squared minus 6x plus 5. So synthetic division is an input-output machine, and it's also a factoring machine because it factors your original polynomial into one factor and a reduced polynomial. And now this one, of course, you can just factor the normal way. You can do the quadratic formula, but it's factorable. 1 multiplies to make 5 to add to make 6, or -6. Is it -5? Wait.
Or
That's -5.
Yeah, -5 and -1.
Yeah.
There we go. Yeah. Okay, well that means p of x is equal to this. Find all the roots of the polynomial. So first of all, the x-intercepts I'm going to write down are -4, 1, and 5, because that's that question. Find all the roots, there's all the roots. Then it also says write your answer in factored form. That's that answer. So you have both answers. Now again, folks, obviously you can get both of those answers from just graphing it on your graphing calculator and getting the x-intercepts. But I'm telling you right now verbally, as a verbal contract between you and me, you need to show the synthetic division to get full credit. In fact, I haven't printed the final exam yet, so I'll just go back into the instructions and write that in. You must show the synthetic division work to get full credit.
Yeah, I was just gonna ask if
Yeah, I'll go in and I'll put in those specific instructions. All right, so now folks, look, now again, what do you notice? What's the rule you know about connecting the x-intercepts to the factors? Right, you're doing the zero product rule, and therefore what happens to the sign of each number? Yeah, the sign changes, right? So these are the actual x-intercepts, but when you put the x-intercepts into factored form, you change the signs. So look at number 12. Here's a function. It's in factored form. Therefore, what are the x-intercepts? Yeah, you change all those signs. The x-intercepts are -4, -2, and +3. Now this is a really fun problem. And of course, when I say it's a really fun problem, it means there's a lot of work to do and it's interesting. So it says graph this polynomial. What's the first thing you could do? Graph it on your calculator, right? But we already kind of know how to graph this because we know we have our x-intercepts. Now, without any other knowledge where to put my x-axis and my y-axis, I suppose I'll just put them in the middle. So there's my x, there's my y. I'll put my x-intercepts at -1, 2, 3, 4. And then my other one is at -2. And then I have one at 3. Now, who remembers how to get the y-intercept? Yeah, you multiply all those numbers together. Now, why is that? You know, that's just a rule. Why is that? How do you find the y-intercept of any function? You plug in 0. And if I plug in 0 into all this, I get 0 plus 4 times 0 plus 2 times 0 minus 3, which means to get my y-intercept, I plug in 0, and I'm literally multiplying up together all the numbers that you have in parentheses. So my y-intercept is now what, -24? I can't quite see that on my graph. If my x scale is counting by ones, like 1, 2, 3, -1, -2, -3, my y scale, in order to get that far down, I would have to count by something else. And you can make the y scale be different from your x scale. So what should we count by? Should we count by 4s? Count by 2s? I don't think 2s will make it. 2, 4, 6, 8, 10, 12, no. How about 4s? So that'd be -4, 8, 12, 16, 20, 24. So I'm counting by 4s on my y-axis. You probably want to show that. If you don't show your scale, it's just pure magic. Right? You're just kind of putting a dash. But there's my -24, there's my y-intercept. Now, at this point, it says, find the coordinates of the y-intercept, done. Find the coordinates of the x-intercept, done. And at least 3 more points. So make a table of values here. We need 3 more points. And the question is, what other 3 points should we get? We need to choose 3 x values to plug in to get more dots to put up here so I can better see how to connect the dots. So where would be some good dots? Maybe one to the left and maybe one to the right so that you can see where it's heading. Like right now, is that thing going to head up or is it going to head down? Maybe we should choose a point to the right. Should we choose 4 maybe? We try 4. Maybe we should try a point to the left of -4 so that we know if the graph is heading down or heading up. So maybe let's try -5. And then how about in the middle here? I mean, it appears as though this part goes like this. But what's happening right here? Does it go up or does it go down? Right? Because it could bounce for all we know. So should we choose -3? That way we know if it's going up or down right there. So these are 3 good x values to choose because they're actually going to give us insight into how to finish the graph. Of course, none of us need insight into how to graph the graph because you all have a calculator and you can just look at the graph. But see, this is how you do it if you didn't have a graphing calculator. So we plug in 4. Now, you know, what are we gonna do? I would just sit there and plug them in one at a time. So if I plug in 4 right now, 4 plus 4 is 8, 4 plus 2 is 6, 4 minus 3 is 1. And 8 times all that is 48, so one coordinate is 4, 48. So that's one of my coordinates, 4, 48. My other coordinate, I'll plug in -5. -5 plus 4 is -1. -5 plus 2 is -3. -5 minus 3 is -8. And negative times negative times negative is negative, and that's -24. So my next coordinate is -5, -24. And then last, I'm plugging in -3, so -3 plus 4 is 1, -3 plus 2 is -1, and -3 minus 3 is -6. And a negative times negative is positive, and so that's just 6. So my last coordinate is -3, 6. So what I just did is the instruction, find at least 3 more points. I just found 3 more points. And you'll notice I chose those points strategically. I was choosing points so I know how to finish my graph. So my one point is 448. I don't have to bother with all my tick marks. I just know that my 448 is going to be up here. So I'm just going to write 448. And my other one, -5, -24, is going to be down here. And actually, I do have that on my axis right now, so I can actually include that one. So there's that point. And then my last point, -3, 6, is going to be up here, -3, and I have to still count by 4s. That's 4, that's 8, that's 12. So 6 would be around here. And there's my next one. So notice those 3 additional points really make my graph pop, don't they? Like now it's plain as day what my graph is doing because I can see the dots, see how to connect them, and my graph really is looking good. And of course you can just graph it on your graph calculator to see. Joseph?
It doesn't matter, because if you plug in 1, you get 30. So it would go down more than the -24.
Oh, that's a good point. This is still just a rough graph, isn't it? Because if you plug in 1, it's actually 30. And so this part of the graph, actually to be accurate, goes down more and then up. Justin makes a great point. By the 3 points that I chose, I was ignorant of that fact. I thought that was a minimum. In fact, it goes down further than up. I wouldn't take off any points on you for that. Of course, if you looked at your graphing calculator and you saw that's what it did, you might as well graph it that way. Okay. 13. 13 works similar, folks. They're asking you to graph that rational function. So what do you want to do first? What should you do first? Graph it on your graphing calculator so that you see what it is. Right, that'd be very good and helpful to graph it on your graphing calculator. So let's all take a look at it. I've got x minus 3 divided by x minus 2. And there's your graph. We generally see what's happening. It's got a swoopy up and to the left and a swoopy down and to the right. My vertical asymptote, I can see it on my graph. It appears to be x equals 2. Yeah, 5 more minutes. And then I also seem to have a horizontal asymptote around y equals 1. Yeah, there. So does everyone agree that the asymptotes, that's what the graph is approaching? So there's that. So now obviously with 5 minutes left, I'm not going to finish going through all of these with you. We are getting pretty close to the material that we just did most recently in our minds. And you can still go back and look at my solutions online. And you can come see me in office hours. And I tell you what, I will finish recording myself solve all of these later today. So at the very least, you can log on and see all the solutions that you like. Let's finish number 13, because that's the one that we're on. So we're going to graph this rational function. It says find the y-intercept, find the x-intercept, and at least 3 more points. Okay. Also indicate the locations of the horizontal and vertical asymptotes. So let's do all that in order, just like we did. Let's start with the easy ones. Y-intercept, x-intercept, vertical asymptote, and then horizontal asymptote. Okay. We spent 2 days on this material. So the y-intercept, how do you find the y-intercept? Yeah, you plug in 0. So if we plug in 0, that'd be -3 over -2, which is 1.5. Now, we just saw the picture of the graph. I'm just going to put my x-y axis in the middle. Oh, and as soon as I finish this, remind me, I want to pass back your test to you. Okay, so my y-intercept is here. Okay, how do you find the x-intercept? You set it equal to 0, but remember what that means. If you set it equal to 0, the denominator multiplies off and vanishes because it gets multiplied by 0. So you're really just setting the numerator equal to 0. You might want to make a note to yourself. When you find the x-intercept of a rational function, you're just setting the numerator equal to 0. So in that case, x minus 3 equals 0 solves x equals 3. So your x-intercept is 3. So far, that's what we have. Okay, vertical asymptotes. Where do you find information about the vertical asymptote? The denominator. Recall, the whole point of rational functions is that the denominator cannot equal 0. So in this case, we set the denominator equal to 0. See how both of those are very good to memorize. X-intercepts is numerator equal to 0, vertical asymptote is denominator equal to 0. So now x minus 2 equals 0 solves x equals 2. Now recall, that's a vertical asymptote, that's a vertical line going through x equals 2. I'm going to draw in a big dashed line there. That's an asymptote. And then finally, the horizontal asymptote is the ratio test, the ratio of leading terms. And in this case, the ratio is just x over x, which is 1. So that means y equals 1 is the horizontal line. So you go to the y-axis to 1, and you put in your horizontal line. Okay, now, you see everything that I have on my graph so far? That alone is going to get you the bulk of the credit for this problem. Because looking at your graph on your graphing calculator, we can all see now just to draw in some swoopies. You draw a swoopie in the upper left, a swoopie in the lower right. So I'm going to do that. I'm going to draw a swoopie in the upper left. That makes sense. I already have a point there to draw it through. So you go like that. And then a swoopie in the lower right, which would be there. And it has to go through the points you already have. The only thing I need now is 3 additional points. Yep, so you'd make a table of values and choose 3 values that you're interested in. So what 3 values would you be interested in? I mean, you could choose maybe a point here for x equals 1 to see where that next coordinate would be there. You could choose some point off to the left and some point off to the right. So I maybe choose -1, -2 maybe, just for fun. I'm going to choose 1, -2. Some point off to the right, maybe 3, 4, 5, maybe a 5. You'll notice I just chose those points to give me a sampling of what happens to the left, to the right, and the middle, just to get more points. And you use your calculator, you plug all that in, and you plot your additional points. Did we do everything? The coordinates of the y-intercept, x-intercept, 3 more points, indicate horizontal and vertical asymptotes with the dashed lines? We did. All right, let me pass out your tests. Okay, now folks, the solutions to the practice final exam are online. You can go to Canvas announcements, all the solutions are there. I will, after my second class today, I'll just keep recording myself to record Irvin. The answers to the last 2 problems, Joshua. Do you have any questions at all? Email me. Come to my office. Write me a letter. Send me an email. Francisco. Jessica. Erica. Chelsea. Joseph. Victor. All right. Did everyone get a test back? Yes, you all did. Great. Boy, I wish I could just stay and do the problems now. Does anyone want to see the next couple if you're not in a hurry? I mean, I'll still record all of them later, but if you want to see them, I'm here, I'm live. Oh, I'll do a couple more if nobody's, All right. So done with that one. Here are 2 formulas. They actually give you these formulas on the test. And they say choose one to calculate the number of years from 1,500 to grow to 3,000 at an annual interest rate of 5% compounded semi-annually. So first of all, how do we choose which formula to use? What's the difference between these 2 formulas? This formula, well, first of all, they both have a P,
Compound.
they both have an R, they both have a T. This formula also has a
Compound is here.
N.
And
N tells you the number of compoundings per year. N is the number of compoundings per year. N, if it is finite, you use this formula. N is finite. So for instance, if n equals 1, that means once per year, that's yearly. If n equals 2, that means twice per year, that's semi-annually, go ahead and write n equals 2. If it happens 4 times per year, that's quarterly, n equals 4. If it happens 12 times a year, that's monthly, n equals 12. If it's 52 times a year, n equals 52, that's weekly. If it's n equals 365, that's daily. So if they give you any finite period for compoundings, then you're going to use this formula, a equals p 1 plus r over n to the n. Only if they say compounded continuously will you use this formula. That is if continuously means n equals infinity. So that means that they're compounding your interest infinitely many times per year. That means continuous. So like instead of giving you interest like water dripping into a bucket, they turn on the stream and it's a stream of water flowing in to the bucket. So the first formula is for when n is finite, like 1, 2, 12, etc. And the second formula is when n is infinite, they use the word continuously and it's PE-2. Okay, so we want to find the number of years. So already, what are we looking for? Oh, hold on. A good idea is to write down A, P, R, N, C. Diagram your unknowns. So find the number of years for 1500. What's 1500? APRNT. You want 15 to grow into 3000.
So that's your starting.
Yeah, so 15 is your principal, what you start with. What's 3000? Yeah, A, the amount at the end. At an annual interest rate of 5%, so R is 0.05. You never use percentages, we always move the decimal twice to the left. Compounded semi-annually means n equals 2. And T, I didn't write anything down for T, and that's because that's the question. Find the number of years. So we're looking for T. We don't know what T is. T is unknown. You can even write unknown. And so when we now move back to our formula and fill all this stuff in, 3000 equals 1500, 1 plus 0.05 over 2 to the 2t. Where is our variable? In the exponent. And that tells us what mathematical operation will we have to do? A log. Because you only have to use logs when a variable is in the exponent. So we simplify. We can go ahead and simplify what's on the inside of the parenthesis. So 3000 equals 1500. That's 1.025 to the 2t. And recall, in order to convert from exponential form into log form, you have to isolate the exponential. So how do I isolate this exponential? The exponential is currently being multiplied by 1500. So you have to divide off the 1500. Which gives you 2 equals 1.025 to the 2t. Many, many times I see someone multiply the 1500 times the 1.025. Why is that not allowed? Why are you not allowed to multiply 1500 times 1.025? Yeah, because of PEMDAS. PEMDAS says you have to do the exponent before you can multiply. So you cannot multiply these two numbers because PEMDAS says you have to do the exponent first and then you can multiply by the 1500. And that in fact tells you how algebra works. That if you want to isolate this thing is being multiplied by 1500, so you divide by 1500. But you cannot multiply 1500 times 1.025 because PEMDAS says you cannot do that. You have to do the exponent first and then multiply. Anyway, now we have this. This is an exponential expression that you can convert to a logarithm. So now this is log base, the base stays the same, 1.025, of 2 equals the exponent. Now, folks, I'm gonna do that step again, starting over from the top here, because I like to rewrite it so that it's 1.025 to the 2t. I like my exponentials on the left and my number on the right, because that's how I always memorize logs. So now I rewrite this as you drop down the first number, log base 1.025. And then you bring the 2 over, and you push the exponent to the right.
Yeah,
So-
that way looks better.
That way does
I
look
was
better.
gonna say, when you did it the first time, it looked totally weird. I do it exactly. the
Yeah,
way you do it.
exactly right. So you can rewrite it. Now, how do I compute this? This is the change in base rule. Your calculator does not have a log base 1.025. You simply rewrite it as log of the big number over log of the small number, and that is now assumed the log button on your calculator, log base 10. And that equals 2t. And we could go ahead and finish solving for t right now before we plug that in and get a decimal. If we want to get rid of the 2, you know you can multiply both sides by 1/2. You could either say t is being multiplied by 2, divide by 2, or you could say multiply by the reciprocal, 1/2. Because that way, that cancels out and you have t equals log 2 over 2 log 1.025. And that you can type into your calculator directly. Let's try it. Parenthesis log 2, divide by 2 log 1.025, and I get 14.03. Which, I'll write it right there, 14.035. Well, it's all the same, 14 years. So you have to wait 14 years to double your money. Questions about that one? Oh boy, oh boy. Almost done, folks. Over here. All right, number 15. It says find all the solutions to the equation. Now notice, folks, see, right off the bat, as soon as you see find all solutions, your brain should be thinking, find a number I can plug in for x to make the equation true. And that's what we're really looking for. Find a number you can plug in the equation to make it true. Josh, Isaac, how dare you leave in the middle of this? I'm totally kidding. Totally kidding. I understand you have to go. You can watch the video later. Okay, so what do we do, folks? The variable's in the exponent, so we need to use a log. And we just rewrite it. This is a very simple one. We just rewrite it, so it's going to be log base 3 of 10 equals 2x minus 1. And I'll use another color to remind you. When you convert from exponential form to log form, the base number drops straight down, and then you switch the other two components. But what is it?
3 and 4.
Oh, then yeah, I want to say, oh no, she left her papers here. Yeah, I don't want to take it from you. Here, let me just write down a note. Because I want you to have it to study. Right? That's Josh 3-4.
Yeah.
Yeah, let me see it. Josh. Practice 3-4. Thank you, sir.
Thank you.
Sure. Okay, so now this, you can just calculate on your calculator using the change of base form. So that's really log of the big number divided by log of the small number. Where again, this is now assume the log button on your calculator. And that equals 2x minus 1. Now, folks, right here, doing all this on your calculator, it can become a little tedious. I mean, no, not tedious. That's not right. That's not right at all. That's not what I'm going to say. It's exacting, right? You have to do it correctly. So one thing you could do is keep this thing as a unit and then finish the algebra. So to solve for x, it's being multiplied by 2 and subtracted 1, so I'm going to add 1 to both sides. So that gives me log 10 over log 3 plus 1 equals 2x. And then I want to divide both sides by 2. And so that's what I end up with, right? So what I would recommend you do is do each step on your calculator, hitting enter after each computation. So you would hit log 10, divide by log 3, enter. and then plus 1, enter. And then divide by 2, enter. Right, that's a really good idea, is just enter, enter, enter after each computation, because that'll make sure that you're doing it correctly. The answer I got is x equals 1.54795. Da, da, da.
What did you do? You did mark that on the log 3 entry.
Yep.
Just one entry.
But instead of typing it all in at once with lots of parentheses, because that's really the trade-off. You either do lots and lots of parentheses and type it all in at once, or you don't have to do any parentheses and you just do each computation at a time. Log 10 divided by log 3, enter. Plus 1, enter. Divide by 2, enter. Hey, what do you think? Would you rather do lots and lots of parentheses or hit enter, enter, enter? I think it works great. That's what I do. You know, maybe a step my way to the answer. Okay, what about you, Celine? Would you rather do lots of parentheses or enter, enter, enter?
Enter.
Yeah, totally fine to do. All right.
When do you think you're gonna be in your office?
What's that?
When do you think you're gonna be in your?
Oh, you know, I think I might just finish these and then come up, so maybe another 20 minutes. Celine, how dare you leave in the middle of this? I'm just totally kidding. I'm just kidding. Gosh, I hope everyone knows I'm kidding when I say that. Class is over. Obviously, you're allowed to leave. All right. So, folks, this next one, it says, find all solutions to the equation. What's the first thing you could do? You can type that into your calculator. Again, set any equation equal to 0, and you can just type it into your calculator and see what the x-intercept is. So here's log of x plus 5 minus log of x, well, negative 2 plus x. And then I have to move the 2 over to the other side, so it's really plus 2 equals 0. So you can set any equation equal to 0. Uh-oh. Let's see a solution. If I had just set that equal to negative 2, uh-oh, I don't see anything. That's weird. What does that mean? I don't see anything. Does that mean I did it wrong? Mean I typed it in wrong? What if I just get rid of that completely and look at my graph? What is that? Whoa, there's my graph. When does that thing equal a y value of negative 2? When does that graph dip down and touch a y value of negative 2? It doesn't. If I draw in my horizontal asymptote or my horizontal line of negative 2, when does my graph touch negative 2? It don't. It doesn't. And therefore, does this equation have a solution? No. Now, we still have to justify that, because right now we just looked at the graph and we saw that there doesn't appear to be a solution. So let's go ahead and justify that. So how do we combine two logs with minus? If you have two logs being subtracted, you can combine them into one log. Wouldn't hurt to write down our formulas. Log A plus log B becomes log of A times B, whereas log A minus log B becomes log of, how do you guys remember? A divided by B, exactly right. So we can go ahead and combine these two logs and call them log of x plus 5 over negative 2 plus x is just x minus 2. I'm going to write x minus 2 equals negative 2. Now again, remember, any positive log goes in the numerator, any negative log goes in the denominator, and that's what we just did. Okay, this is written in log form. What's the base? What's the base number of this log? 10. Because it's not written as a 10. Okay, well, one thing I've said is that if they give you the problem in log form, convert it to exponential form. If they give you the problem in exponential form, convert it to log form. So right now, we're just going to convert this back to exponential form. So this means 10 to the power of negative 2 equals all that. So 10 to the power of negative 2 equals x plus 5 over x minus 2. 10 to the negative 2 you can do on your calculator. You can either say 10 to the negative 2 is 1 over 10 squared, which is 1 over 100, which is 0.01. By definition, 0.01 is 1/100. So that's 0.01. Because x plus 5 over x.
We just type in on the calculator 10 to the negative 2, it automatically.
Yeah, it'll just automatically give you 0.01. Okay, so now we just want to solve this equation. Again, the pesky part is the denominator. How do we get rid of a denominator?
Multiply it out.
So now we get to cancel those, distribute the 0.01, so that's 0.01x minus 0.02 equals x plus 5. Now notice at this point, this is just standard straightforward algebra. Nothing mysterious here. I push my numbers to the right, giving me 0.01x equals x plus 5.02. And then I bring my x's to the left, which is minus 1x. So that's negative 0.99x equals 5.02, which gives me, dividing by negative 0.99, coming over to here now, it gives me x equals negative something. Five. 102 divided by 0.99. That gives me negative 5.07 repeating. Now, on the last test, I noticed a lot of people, when they did a log problem, as soon as they got to a negative number, they wrote extraneous. That's not correct. You can have x be a negative number. X can be a negative number. That's totally fine. What you can't do is log a negative. You can't log a negative number. And so, while this is a legitimate answer, I would have no reason to discard this answer. I can't just look at that answer and say it's extraneous. But then I actually have to plug it into the equation, and that would give me log of negative 5.07 plus 5 is negative 0.07, and then log minus log of negative 2 minus 5.07 is negative 7.07. This is what's not allowed. I can't log a negative number, and that's what makes this solution extraneous. This solution is not extraneous because it's negative. It's extraneous because when I plug it in, I log a negative. And that makes it impossible. So my only solution is extraneous, which means the original equation had no solution, which we already saw graphically, because the graph, which looked like this, never got down to negative 2. So that's nice to see all that in perspective. Oh boy, just a couple more. You guys questions about that one? All right, solve the system. We'll just quickly glance at this one because we did just recently solve systems. We have x plus 5y equals negative 5, negative 7x plus 6y equals 35. Now you'll notice the instructions don't say how to do it. Yeah, so you can do substitution, elimination, you could graph it. But no matter which method you use, substitution, elimination, or graphing, you need to actually show that the two numbers you find make both of those statements true, because that's the definition of solving a system. Just find a coordinate that you can plug in to make them both true. So I'm just going to go, oh, you can do the inverse method too if you want. You can do matrix inverses. I'm going to go ahead and do elimination, eliminating the x variable, because I can just multiply that top equation by 7. So it'll be 7x plus 35y equals negative 35. When I add them together, the x's cancel, the 35's cancel, and I get 41y equals 0. And therefore, dividing up to 41, y is also 0. Now that y is 0, I can go back to either equation and plug that in. I'll do the first one, since it's just x plus 5y equals 35. And if I plug in 0 for y, I plug in 0, 0. And so x equals negative 5. So I have x is negative 5, y is 0. First thing I do is write down my answer, which my answer is apparently negative 5, 0. But even that right now is just a guess. It's just a very well-educated guess based on some algebra that I did. I would still need to plug it in and see if both equations are true. So x plus 5y equals negative 5, and negative 7x plus 6y equals 35. If I plug in negative 5 and 0, this becomes negative 5 plus 0 is negative 5. That's true. If I plug in 35 plus 0 is 35. That's true. So yes. Only at this point right here am I done with the problem. I showed that both of my equations are true when I plug in the coordinate negative 5, 0. Now, the next class is about to come in, so I'm going to stop this video. And you can choose the next video on the list. It will show the rest of the solution.